previous video, we looked at the challenges associated with running deep learning algorithms on big data. Let's take a look at how we can actually look to solve for them. First and foremost, what we need in terms of deep learning on large data is data parallelism. And in doing data parallelism, we need to think carefully about how do we take the deep learning network and are we going to partition that, in which case we run into some complexities. How do we handle the weight updates, etc. So let's talk about what options are available for distributed deep learning. We want to get to a stage that the training effort that's required, right, in terms of coding, when done on a single GPU, it should be as commensurate to the same to the effort that's required for doing the training on multiple GPUs on a single machine or multiple GPUs across a cluster of machines. If you get to that stage, then the incremental cost of coding, right, when going from small data to large data is negligible. And that's what makes it conducive for us to run deep learning in a truly distributed sense. So how can we do this? So there are approaches that were proposed before that have been implemented. Some are popular, some are not. So let's take a look at two such examples, both in the open source community. One, as part of Google's TensorFlow project, which is itself one of the most popular deep learning open source projects, they came up with this notion of what's called as a distributed TensorFlow. So that took TensorFlow and made it run on multiple different machines, but to solve for the weight problem, meaning to be able to exchange weights across the different model instances which are on different machines, they introduced something called as the parameter server. And the parameter server was like a common set of might be one or maybe a cluster of servers based on the scale, and that hosted all of the weights or parameters which are necessary for the deep learning network to work, and the individual machines would keep posting their updates back to the parameter server without having to wait for each other. So that kind of a model became quickly, limited in terms of scale because the extent of communication that was required between the deep learning training machines and the parameter server was happening was actually quite expensive, because all the communication of data was happening through the network interface, and that, as we know, is actually lower latency than the speed at which GPUs can run for sure. So, and the amount of chatter that was involved, chatter meaning the amount of data that was actually sent out over the network, was significantly higher compared to this alternative approach that we will spend some time on in the rest of this week's lectures. So this alternative approach was first designed by Uber and then later on made open source. It is called as Horovod, right? What Horovod did was to make a distributed deep learning framework generalizable that can apply to multiple different deep learning frameworks or libraries behind the scenes, right? And most importantly, was designed in such a way that it didn't use any external servers or extra servers like the parameter servers, and this removed one of the significant sources of bottleneck that was there in the prior approaches. So what did Horovod do? First and foremost, it said that I want to be a neutral layer, right? Just like Keras is neutral to whether you use TensorFlow or PyTorch behind the scenes. Likewise, Horovod also said anybody who uses one of these popular deep learning networks should be able to, not networks, deep learning libraries, should be able to benefit from operating on single GPUs or multiple GPUs on a single machine or multiple GPUs on a cluster of machines, doesn't matter, with minimal coding effort, right? So Horovod said from the get-go, I will introduce my layers in such a way that I can ensure cross-compatibility with TensorFlow, Keras, PyTorch, Apache MXNet as well, right? So that became like decision point number one. The second thing is Horovod leveraged a particular way of doing parallel processing, parallel programming, that's called as MPI, or message passing interface. MPI is actually a standard. Think of it as a message passing library specification, which is done in the open source community. Rather, it's become open source now because it's a specification that everybody adheres to, and it became most popular early on as one of the key ways in which parallel programming used to happen, right, for scientific computations. So its core abstraction is one of being able to do memory-based processing, but in a cluster of machines where the memory is distributed. So think of like a typical cluster of machines that we've talked about so far in the context of divide and conquer, map reduce, big data. That is actually also having memory that's distributed, right? So it's not shared memory in the sense that you can't access all of that memory as though it's one memory. That doesn't work. You have to think in terms of distributed memory, and for that distributed memory, you have to make some computations on top of it, assuming that the data is all available in memory or can be exchanged via memory. So if you notice that there is a similarity, right, to the MapReduce paradigms. So how does it contrast? The most important way in which it contrasts is that with message passing, you can be as pinpointed as you want, or you could be as general purpose as you want, right? If you take it to the general purpose extreme, you're effectively saying any machine is as special as any other machine. So therefore, all machines execute and all machines complete and all machines gather their information. That introduces a barrier, and then once that's done, then you start the next process. So that kind of a setup, every machine is equally as special as everything else. So that's massively parallel processing, or the MPP. That's what MapReduce is good at, right? Whereas with the message passing interface, you could do point-to-point communication. You could treat some machines as more special than some other machines, and you could designate those machines to do extra work or to communicate on behalf of the rest of the job, etc., etc. So that point-to-point communication is one of the key ways in which MPI allows for a slightly different type of workload than MapReduce. But the fundamental notion of scattering an operation, or basically scattering the data from an operation, gathering data from an operation, all of that is very similar to how shuffle works in MapReduce. Okay, so within MPI and therefore within Horovod, each parallel process is denoted by both a rank and a local rank. A rank is basically a global ordering of the process. So imagine if you have a Spark cluster of 3 executors, rather let's say 3 worker nodes, and each worker node has 5 executors, which makes 15 executors in total. So if you assign each executor to one GPU as an example, then you would have a rank of you would have a size of 15, and you would have rank going from 1 to 15, which means the process 1 in executor 1 will be given a rank 1, process 2 will be given a rank 2, process 3 will be given a rank 3, until process 5 is given a rank 5, and with that machine is done. Then the next machine is picked up. With the next machine, process 6 is given a rank, process 1 is given a rank 6. So likewise 6, 7, 8, 9, 10 for that second machine, and 11, 12, 13, 14, 15 for the third machine. So that's rank, which is basically a globally unique incrementing counter. Local rank is basically the same thing as a rank, but local to a machine. So within a machine, the 5 processes have local ranks of 1 to 5. Second machine also has a local rank of 1 to 5. So that's like 2 of the specific concepts rather. Separately, MPI itself supports the specification of like 5 different types of operations for reducing, for bringing the data together. Now, notice that MPI is a specification, which means there are implementations of MPI, and one of the most popular ones is something called as OpenMPI. Horovod also implements the MPI interface. In fact, it uses OpenMPI. So the standard MPI operations here are all reduce, which makes a bunch of operations happen on aggregated on an aggregate basis across all the available processes, all the available ranks, basically. All gather is where you bring the data back together. Broadcast is where you go from one machine to the entire machine. So you're broadcasting from one machine to the entire cluster. And then likewise reduce, scatter, all to all. These are all just variants. You don't need to understand this in detail. I'm just giving you a sense of how MPI differs from let's say MapReduce. Okay, so how is Horovod used in practice? First and foremost, you would take a process of Horovod, which is basically a process of the deep learning model training, and assign it to one GPU. So there's a 1:1 mapping that's recommended. The size here is basically the size of the entire processes, which is basically the size of MPI, and also therefore the parallelism that's inherent to Horovod. So all of that therefore become the number of GPUs that you have available in your cluster. Notice that your cluster could also have CPUs, and we'll come back to that. Like typically you would use the CPUs for Spark to do its ETL as an example, transform the data, prepare the data, etc. Once it reached a certain stage, right, where the data is prepared and you now have to train it, at that point you can hand it to the GPUs. Okay. Now, batch learning is necessary. Now, this is true for all distributed deep learning frameworks with data parallelism in it, because the moment you don't do batch learning, you do what's called as online learning, then you're just having too much chatter on the network. Right? Online learning is basically saying every single data sample that I read from, I adjust the weight. So, one thing I should mention here is that in these kinds of data parallel deep learning, distributed deep learning frameworks, what's really happening is that the model that you're training is copied for every process. So if you have like the cluster of 15 like I was talking about, the size is 15, which means you have 15 GPU processes, and each process has its own model copy. So you've taken the model and you've copied it over, and then each iteration or each epoch of training will go adjust the weights that's corresponding to that particular GPU only. Now, as a result of this, the model that's in every GPU has already become different, because every model would have gotten updated by its own GPU based on that GPU's data, which is different from other GPU's data, obviously, because it's data parallel. And as a result, the model would look different. Now, if you didn't have this, right, if you had to exchange messages all the time for every single record, then you would have enormous amount of chatter in the network, and that will make it extremely prohibitive. So that's why I'm saying that batch learning is necessary. It's not online learning. Now, batch learning is less accurate, obviously. It basically, the learning happens in steps. And so, to compensate for this batch learning, it's necessary to actually increase the learning rate. And usually the learning rate is increased by setting it to the size of the cluster. Size of the cluster is basically the number of workers in the cluster. Right? So that's the second best practice in terms of usage. Then Horovod has its own abstraction of an optimizer, which is called as a distributed optimizer. Behind the scenes, it actually delegates the gradient computation to the appropriate gradient algorithm. So gradient algorithm is basically the algorithm that dictates how the losses get computed and how the adjustments to the weights happen. Right? So it's a gradient across the optimal function, and therefore you're descending the gradient. So that's why it's called gradient descent, because you're descending towards a minima. Minima is basically a minimum point which is optimizing for the least error that's predicted by your network. So there are many gradient descent algorithms which are commonly used in deep learning, and each deep learning framework has its own implementation of such algorithms. So instead of Horovod implementing yet another set of or creating yet another set of implementations like that, it's just created a distributed optimizer which uses the appropriate deep learning framework's backend gradient computation to ensure that that is not reinvented. But once that step is done and the weights are computed, then it uses an all reduce and all gather set of algorithms to average out the gradients, to make sure that all the models actually have the same weights as a result of the step, and then all of them have the average of the gradients across every single instance, right? So that there is no single instance that's given special treatment. Because every worker has its own copy of the model that it trains on, it's not necessary that you have to checkpoint on every worker, right? That's a waste of effort. So typically what happens is you could just checkpoint based on one of the workers, which is worker node 0 as an example, and then you could use that as a basis for recovery in case something goes wrong. Finally, Horovod actually has a mechanism for auto-tuning, And that is very powerful because you could use that to improve the runtime performance by leveraging that auto-tuning automation for determining the right parameters for Horovod to work. Horovod also has parameters, obviously, because it's not just a dumb abstraction on top of deep learning frameworks, right? It's actually trying to figure out when to distribute, how much to distribute, etc. So that is an auto-tune exercise that you can easily leverage and benefit from. If you don't want to do that, you can always do a manual run. Okay, so now putting all this together, how do you do data parallel distributed deep learning? Horovod can be used on top of Spark, right? So that becomes the way forward. So this enables the distributed deep learning of data sets. Now, Horovod Spark also takes care of the data exchange that's necessary between the Spark data frame and the native formats of deep learning libraries. So that is pretty cool. And in fact, Horovod also takes care of the model training and the model evaluation as steps that happen natively within Spark. You don't have to worry about spinning up a brand new cluster and managing that. So that's a big headache off the shoulders as well. Now, typically the way in which the deep learning training makes progress is by constantly adjusting the parameters, the weights, etc., and then coming back and evaluating the threshold, right, of how much error that you can tolerate, and then accordingly terminating the node, or terminating the process. So that typical training, if you do using PyTorch or Keras, right, then you can use the inbuilt estimator that Horovod has. That makes it very easy for you to work with the custom training needs that you might have. And we'll see an example of what this means in the next slide. But if you need to do some custom extensions to it, which is not supported by the estimator API, there's also the regular run API that's available, which is Horovod run. You could use that as the lower level API, and then you can override all of the standard details that the estimator API would have taken care of. So with that, let's take an example of a Horovod and Spark example, Horovod and Spark program. So since for some of you this might be the first time that you're seeing a deep learning code, you might not understand a lot of these terms and jargon. That's okay. I'll just give some top level examples or definitions of these, but then for more details you can just look it up online. So Keras, like I said before, is effectively able to provide abstraction across both TensorFlow and PyTorch if you want to train in a way that's agnostic to what the underlying deep learning framework is. So Horovod itself can be imported as well. Horovod.spark or Keras as HVD. Now the model that you have, the deep learning model that you have, in this case is got 4 layers. It's not really a deep learning model because it's got a small number of nodes only, but that's okay. We will make do with this for this example. The Keras initialization is also set the gradient descent algorithm that I will use. So in this case, I'll use something called as the stochastic gradient descent or SGD. The learning rate itself is unscaled, meaning I've not multiplied this by the size of the cluster yet, right? But you should do it in order to get the right adjustments to the rate at which the learning happens. I'm going to use a specific loss function that's called as binary cross entropy. That's beyond the scope of this particular week's lectures to actually explain, but look it up online. All of the experiments and the log that comes from it, it's getting stored in HDFS, or you could also store it in GCS, it doesn't matter. So within Horovod, there is an estimator API like we spoke about. So it's called the Keras estimator. And that takes a bunch of these columns, rather a bunch of these parameters, and you can adjust it and train it, etc. Like adjust it and tune it, rather, not train it. So in this case, I've just said use some 4 processes, store the in-between experiment runs in HDFS in this path that's shown here. Use the optimizer that I've already defined, which is the Keras optimizer SGD with learning rate 0.1. The loss function is binary cross entropy. The features that I'm going to train on as features, the dependent variable is y, and batch size is 32, etc., etc. Right? So there's a configuration of an estimator, and then once this is done, I can go apply it as a transform on top of the training data. The training data I'm assuming is a training data frame, which is just a regular Spark data frame. And then when I do the fit function, I'll basically get back a transformation. And that transformation, I'm going to set like the columns to predict, so that the dependent variable is actually called as a predict. And then once the transform is ready, I can use that to apply on the test data, right? So that becomes my final prediction for what the model is predicting as an output. So in this case, like you see, the Horovod specific layers are the estimator, right? And then the rest of the stuff is actually exactly the same as what you would do with Keras if you didn't have Horovod at all. So that's the power of actually incorporating something like this, which is agnostic to the underlying deep learning library. Okay, so with this we have just come to a close on the discussion on Horovod. Let's meet again for the next video when I talk about the last remaining challenge that was highlighted earlier. Notice that with Horovod and Spark, we now have access to distributed deep learning, where the deep learning architecture is not partitioned. In fact, it's made a copy of for every GPU, and the weight update is taken care of by the Horovod optimizer, distributed optimizer, which is itself embedded within the Keras estimator. So that way, you can use the estimator API itself to hide away all of this complexity for you. It just works behind the scenes, right? The data exchange between Spark data frame and the deep learning library, that's also taken care of by Horovod. In fact, there is I forget the name now, but there is a very specific data loader that's available from Horovod again, or from Uber again, which makes that particular data exchange possible. So that is regarding the second challenge. Let's go back and look at the third challenge, the Spark utilization, rather the GPU utilization of the Spark cluster. So this is something that Horovod enables using MPI. Unlike MapReduce, which has a barrier synchronization which is much more stricter, in MPI point-to-point is possible, and point-to-point exchanges of weights are also possible. So what this allows you to do is allows you to treat different machines in a way that's special. You don't have to treat all the machines in the same way. So when you are going through the training, the skew doesn't affect you as much. It still affects you, of course, but not as much, because you can continue to use MPI for weight adjustments between machines which are ready. And then the tensor board related visualization in the front end, that is something you cannot do much about with Horovod. You'll have to figure out some other examples for it, some other ways of solving it. So the last example of the last challenge that we saw was deep learning scoring on big data. So that's what we'll spend time on as part of the next video.